Hello, my name is Elsa and I'm here to welcome you to this short series about citizen science and the Dive-In project. Today with me there is Gjino from Croatia, from UR Institutes, and today we're gonna talk about microbial fuel cells or batteries out of mud, right? So thank you, Gjino, for being here. Can I tell you to explain a bit more about yourself and your institute, please?
Thank you for having me. It's a pleasure to be here. As mentioned, Gjino Sutic. In my vocation, I'm biotechnologist and also biological artist. I produce a lot of projects, and I'm actually directing a cluster of 3 organizations. First one and the main one would be UR Institute. It is NGO that started from citizen science as its root, is devoted to applicable scientific research, specifically biotechnology and experimental electronics, and also popularization and integration of science into society and culture. So Institute is devoted to non-profit research. Next to the Institute, we have a spin-off company called Gjino Industries, which is devoted to development of innovative technologies. So it comes from my name, but also Gene Zero, which would be like the first prototype generation of technologies. Okay. So that's the etymology of the company. So whenever we come with something that could be useful and maybe turned into a product, then the company takes over this commercialization aspect. And from relatively recently, 2 years ago, I took over running Association of Innovators of Dubrovnik-Neretva County, which is focused on popularization of innovations, trying to provide support to innovators and, in general, the value of this creative sector. Which is a little bit problematic, especially where I'm coming from, Dubrovnik, Croatia in general, which is devoted to tourism. So it's a little bit of counterculture, trying to stimulate and provide and to incubate development of new industries and creative industries. Altogether, we merged these 3 organizations into a platform called Innovation Generator.
Okay.
So yeah,
that's really interesting. You do a lot of things. Unstoppable. Yeah. Okay. Can I ask you, so at this point, what is the citizen science for you and for your organization?
Beginning and the end. In general, as mentioned, I started from citizen science aspect, so it's like hard-coded into the spirit of all of the organizations that we are running. Citizen science as a topic has really evolved recently in the last few decades, and it's continuing to evolve. So it's not so easy to sum up what does it mean. It's always a subjective question. In my opinion, we have 2 different subcategories of citizen science. One would be the classical definition of citizen science. Citizens conducting some form of scientific research. Classical examples would be bird watching, where normal citizens who don't have scientific background monitor the population of birds, also sometimes discover new species and so on. So it's hardly connected to the ecology. Okay. But also we have another side of the citizen science that would be in this first aspect, actually citizens are providing the data for the scientists that can add everything to scientific knowledge of our society in general. And the other aspect would be citizens practicing science by themselves, and especially science related to engineering, making discoveries. So innovators, inventors, they are all scientists. And this other aspect of citizen science comes from do-it-yourself and do-it-with-others experimentation. So that would be like my definition in general. My favorite example from this aspect would be, for example, Hedy Lamarr, which was an amazing Hollywood actress, but in a spare time, she developed innovations of her own. And actually, one of her inventions is the basics of all of wireless communication that we use. This frequency hopping technology that we use in Wi-Fi, Bluetooth, everything. So this illustrates the power of citizens being engaged in scientific fields.
Of course, everyone can have a role, even without knowing a lot about a subject, but they can get in close to that in a do-it-yourself way. It's really, really inspiring. Thank you. So maybe you remember the moment or the person you get passionate about science?
Uh, yeah, of course I do. I'm a little bit introverted, so always I spent my childhood playing in the garden and so on. So for me, my earliest memories come from discovering world around me. I'm really grateful. So the first person who inspired me to practice science was my grandmother, who used to bought me lots of encyclopedias and different kind of science-related books that like opened this whole world of discovery to me, like intro into the equipment, techniques, methodologies, and so on that you need to practice science. Also about the diversity of scientific fields and the field of technological developments. So that was always like intriguing for me, and I was really great. So I started with do-it-yourself experimentation when I was really young, even before going to school, and I'm really grateful I had. Some of my professors were really amazing in supporting my interests. In primary school, it was like biology teacher. At universities, was microbiology teacher, and so on. They have been really supportive.
That's cool.
And open to questions and to self-experimentation, discovery, and so on, which is really the most important thing, especially today, because you can get the knowledge by Googling.
Yes.
But how to use the knowledge, how to understand the depths, and so on, you need community, some support to exchange ideas, to discuss everything.
Yeah, it's true. Nowadays we have a lot of more of tools to get involved, but create a community where we can share the knowledge and make mistakes all together to learn.
Exactly.
I think it's the best option ever that we can ever have. Yeah. So, what do you think can be the future for citizen science and for the population with the citizen science?
No, I see a lot. So, like to begin with, I think like citizens in the very beginnings of scientific development, citizens were really engaged in developing science. So, actually, every scientific field came from nothing. So first scientists in some specific fields actually came from different domains where they were like total amateurs. Like, for example, Leonardo da Vinci discoveries of anatomy and flight technology and so on. So he wasn't aero engineer, you know, so he was a citizen. So in the very beginnings, there was this amazing integration of society, technology, and science. And then with the growth of scientific body, there is now a million fields, subfields, and so on. This like whole body of science and knowledge is so huge that it's not easy anymore for a single person to comprehend the scope. So the science went into this diversification and specialization. And through specialization, the gap was created between scientists and science in general and citizens. And now, recently, in the last few years, I feel that society is again trying to bridge this gap. So we have pop-up of new practices related to citizen science, such as maker culture, do-it-yourself culture, and so on, which are, and also spaces, communal spaces, communities devoted to exploring, such as maker spaces, fab labs, different community spaces which do prototyping, experimenting. So these are the current practices. And with the trends, I see that finally we are again merging this gap between society and science. Yes. And also I see that actually the academic institutions are opening more and more because they also see the necessity that even though it's amazing what they do in scientific research, it needs to be communicated to general citizens. And so, so involving citizens in scientific process, open door policies, and so on, are the current trends and the future of citizen science. So in my opinion, more and more citizens are going to be engaged or in one or the other way into scientific fields.
Let's hope so. But I'm sure that if we have people just like you working on that, it's going to be more and more popular. So let's hope so. I have one last question, but I also know that you took something with you. So later on, we're going to also see something. Yeah. But can I ask you at this point, how do you think it's useful for young people, the citizen science, to get involved and to get closer to science?
It gives them perspective. That's to begin with. Okay, like each one of us, like children are born with curiosity, So educational systems should nurture curiosity and provide the space for youth, for kids to explore and to develop their own interests. But it's not easy to develop interests if you don't have insight into the scope, the whole palette of interests and the fields that exist. So usually, from my experience, I was also teaching in high school for a bit chemistry and biology. Kids in schools, they don't have the insight in current trends, and they don't have connection or insight into what industry does in general. So for them, if you ask a primary or high school kid what science is, they will just list scientifical subjects that they learn in school. And usually, even though if they can be the best students ever, even for the best students ever, it's not easy to relate that knowledge with different domains and the real world around us. So citizen science comes into this topic. Citizen science enables this interdisciplinarity, connection of scientific discoveries with engineering skills. Also, it provides hybridity. In my opinion, when you merge two different fields, that's the only way how to create innovations. So, next to providing knowledge to youth, which classical educational system does, I would say the most important thing of citizen science that can provide to youth is development of way of thinking. So it nurtures creative thinking, constructive thinking, also critical thinking, which is really important, especially today where we are overwhelmed with information. We can have the access to world knowledge with one tap on mobile phone, But like how to approach everything critically, how to filter out important information from all of this noise. That's not an easy skill. And citizen science actually can provide this. So it's an amazing addition to normal educational systems. Yeah.
Gjino and I were talking about the project he's carrying out with his organization to involve people into citizen science. So maybe can you show us some experiments, some example of what are you doing in the practical way?
Yeah, of course. For today, I prepared a short experiment that you can find in our book, Dive In. It's how to make microbial fuel cells, or how I like to call them, batteries made out from mud. It's a simple experiment that everybody can do at home. It requires extra simple materials. It opens curiosity for youth and for all of the citizens for the fields of bioelectronics and microbiology to which it is related. Also, it's related to experimental methodologies of energy production, which is also current and open topic. So this technology has amazing potentials that I can talk a little bit about while I'm showing you how to make it practice.
Yes, please.
Yeah. So in regard of the materials, as I mentioned, it's really, really simple. All we need is a small container with goggly eyes, if possible. Small container that we will use as a casing for the battery. Okay. We need wires, of course. If we are producing anything that gives electricity, we need conductive material to carry the electricity. We will need to make electrodes. I'm going to explain a little bit more into details, but just to illustrate, we're going to use aluminum foil for one, and for the other one we are making do-it-yourself graphite electrodes by drawing it with a pen. Actually, we are producing graphene as a material in its simplest possible form. There is differences, but later on I'm going to go into that. So then we need to use a little bit of mud. Here we collected soil samples. We are using the mud not because of the mud itself, but because of the bacteria that reside in the mud. As we all learned in school, if we can remember, in soil we find decomposing bacteria, which can eat everything organic to turn it into a soil. Specifically, we are interested into bacteria which can eat cellulose, which is the most abundant biological material. So all of the plants, trees, leaves, paper that we make from from trees are made of pure cellulose. As humans, we can't digest it easily, but for bacteria, that's not a problem. But to be able to digest cellulose, we need conditions where there is no oxygen inside.
Okay.
So this is what we are actually going to produce in this container, a small microenvironment with this mud and bacteria that will push out all of the air inside, so that we have anaerobic conditions without oxygen.
Perfect.
So that this bacteria can activate and eat the cellulose. And while doing so, they do a lot of chemical reactions there. And if we hook them to a wire, to the electrodes, we can actually steal the electrons from these chemical reactions, because in comparison to humans, we do our digestions inside of our stomachs. And bacteria does everything outside of its organism. So all of these chemical reactions are happening outside. So what we are trying to accomplish here is to steal the electrons from the bacteria while it's eating cellulose to produce electricity.
That sounds amazing.
Yes, it is, and it's a really amazing technology and a huge potential, as I mentioned. We can use this to generate electricity. It's still in its developmental form, so there is a lot of optimization needed. So that's why it's important that people experiment with this technology, so that we can produce higher voltages, more power from this technology. It's totally green, so it eats biological waste. We can feed the battery with any kind of biological waste, like cellulose is just the example. You can use like leftover food at home and so on to feed these batteries, microbial fuel cells. Also, it can be used as a biosensor. In this instance, we are going to be making battery inside of this contained jar. But we can also play with the design so that it is flow-through. And if we have a flow-through design, we can hook it up to any flowing water source. And by doing so, we can use these bacteria here as a sensor to sense how much organic waste is dissolved in this water. So the more water is rich or polluted with organic waste, higher voltage the battery will produce, the sensor will produce. If the water is extra clean, purified, they won't produce any electricity. So it's really good for the industry, because most of the industries produce residual water, wastewaters, and with this we can sense if the water has been purified or not properly.
Wow.
So yeah, it's a huge
lot of
potential.
Solutions actually in this.
Yeah, to start with practical aspect, as I mentioned, we need a container. We need a wire. We need two electrodes. One electrode to make this to close the circle of electricity, and so we use two different kind of materials because single reason, how compatible it is with the bacteria. For example, my favorite and easiest to use bottom electrode is graphite electrode. So what we have done here, I prepared a little bit in advance so we can fit everything into this small tutorial. You take a container you are using, you draw a circle around the bottom, and when you have drawn a circle, the container bottom on the paper, then you need to use the pen. The best pens are the ones which have more, which have like less lead inside and more carbon inside. So the carbon-rich pencils are the best. Then you actually need to draw the electrode, and we do so by squeezing the pen really hard. What's really important here, that we need to draw it like the whole drawing on a paper needs to be really black and glossy. If it's black and glossy without any holes, like for example this is not good and this is amazing, we actually connect the layers of the carbon graphite from the pen next to each other so that there is no gaps. And if there is no gaps, carbon is also a conductive material. It can conduct electricity. To check if we did it properly, we can use a multimeter. It's like really useful tool and the basic tool if you are gonna go experimenting with do-it-yourself electronics. Since carbon is not a perfect conductive material, like in comparison to copper, which we find in wires, it produces lots of resistance. So to measure the conductivity, we need to set the multimeter to measure resistance. Actually, we put it to maximum, and then we just look if the number changes on the screen. So, like if these two electrodes we use for testing, if you can see, like now they are disconnected, there is nothing moving on the screen. When we take them together, we will see that they conduct electricity. When I connect them to my body, we will see also some conductivity, because human body full of water and it conducts electricity. Then if I want to test the paper, if I put it here on the white part, it's not conducting anything. If I put it on this electrode, also it's not conducting anything. And if we did this properly, yay, there is some electricity. So we managed to make a conductive material by pen and paper. What's really interesting and good about this, carbon is the base of all life. So it's a biocompatible material. So when we add mud to this, bacteria from mud, it won't kill them. So they can actually live on this electrode. They will make a nice small layer called the biofilm. So it's the best possible material that is compatible with living organisms and bacteria. So when this is done, we need to cut it like we did here. Then we need to connect this somehow to a wire. So to do so, we use usually hot glue. Hot glue is the best solution, but we need to be really careful when we are experimenting with this. This is like the trickiest aspect. It's easy, but it's tricky a little bit. So we need to hold the wire really hard and really close to the material.
They get to touch each other.
Yeah, so they need to touch each other, and the hot glue needs to go on top of that. If we are like, if they are not touching, the hot glue will go in between, and it will isolate the wire. It will not connect the two. So yeah. After we have connected the wire to the electrode, we are actually making a small sandwich. So first the electrode goes to the very bottom of the jar we are using. What I wanted to mention, the amount of electricity this battery produces only depends on the size of the bottom electrode. So if you want to produce more electricity, you can go with a bigger jar. And I want to do comparison. This is actually like small scale composter that produces electricity. So if you want to be ambitious, you can make a big composter in the garden which can produce a lot of electricity. So we need an electrode on the very bottom. Then we need a little bit of mud. The best mud to be used is that from lakes or rivers, because it already has a high content of clay inside and this anaerobic bacteria, but any mud will work. So we put just a little bit of it on the very bottom. It will provide the battery with needed micro power plants of bacteria. Then we need to add some food for the bacteria. In this case, we prepared some recycled paper. So you can use recycled paper, which is actually pure cellulose, or you can use old leaves from the garden, from the outdoor, or any food waste, whatever botanical you have can be put as a food for the batteries. Then we add a little bit more of mud, just for the reason that it holds together these leaves and paper, which would usually float on the very top. So it's just to add a little bit of gravity. Weight to this. Then we have the top electrode. For the top electrode, so the goal here is for the bottom one to enable biofilm of bacteria to connect to it. But for the top one, to make the difference, we need actually disable bacteria for sticking to it. To do so, the best thing to use is a little bit of aluminum foil, because aluminum foil, that's why we use it in the kitchen, is not friendly to bacteria. It will actually kill off any bacteria that tries to connect to it. So we just fold a little bit of foil on the wire. We don't need to stick them together because it's easy to squeeze. And we have our top electrode. And now to produce the difference in between the two, we need to enable the flow of ions and electrons in this battery. We just need to add water. So this is normal water that we use for drinking. And we have our battery.
So curious about it.
I just made a small hole through the lid. Okay, and just to mention, so now when we have assembled this, we have a small amount of bacteria on the biofilm. But with time, since we added food, bacteria will grow, the biofilm will grow. So actually the amount of electricity produced by this battery will grow in time. So in a week time, if we leave this at room temperature, it will be at its like maximal capacity. And to measure the electricity produced by the battery, we can also use a multimeter. In this instance, we are not putting it to measure resistance. We are putting it to measure voltage.
The voltage. Oh,
okay, this is not really nice.
Yes, it's nice, right?
0.68 volts,
It's not that
which
bad.
which is really not that bad. This by itself can even power small electronic devices that don't require too much energy, but let's say we should hook up 3 to 4 batteries such as this to power a remote for TV.
It's a start.
It's a good start, but if we make it bigger, we can produce more electricity. But as I mentioned, in a week time, the voltage will grow. So the maximum I got from these small containers was 1.3 volts or something like that, which is actually equivalent to most of the standard batteries that we use.
Of course, that's really interesting. That's really interesting because also you add more subjects all in one experiment. I can hear, electronical devices in a way, biomaterials, soils, biology from their living things. So I think it's really, really cool. I think that children get crazy about it.
Yeah, it's an amazing hybrid interdisciplinary example that can actually open a world of electronics, chemistry, biology, ecology, energetics, sustainability, and also this system thinking about this is a closed system, how everything, all of these components interact. It can open a world for you, and it's really simple. Everybody can do it at home, so I would highly encourage everybody to try to do that.
Lovely. I'm so curious about the toolkit now, even more than before. So let's hope that it's gonna be a real surprise for everyone. So thank you so much, Gjino, for being with us and show all of this.
Thank you for having me. It was a pleasure.
Thank you, Gjino. Thank you.